Hello everyone, my name is IOcken. I am enrolled in ECE 331, 311, and 341, and today I will be talking to you about the amplifier and speaker system. Alright, so quick outline. First I will discuss the signal, both its input and output, and how they are affected throughout the circuit. Then I will talk about the amplifier circuit, and then I will talk about the speaker itself. So first we have the signal. We have our V in going into our LTI system, which is the audio amplifier, and coming out is V out. Our V in this case is a cosine wave, an amplitude A, and frequency omega naught. And our output then becomes that same input multiplied by the frequency response at that frequency of our input, and then goes through a phase shift of that frequency response at the same input of the sinusoid. And you can see that at 1 kilohertz, which is our given frequency, there is a value that comes out as well as our DC. And over here we have the input wave, which is a solid red line, V in, going from 5 to 5 millivolts peak to peak, so 10 millivolts total. And then you have the V out signal, which is phase shifted by a factor of pi radians and is amplified by the frequency response by about 4. Now I will talk about distortion, which is where you increase the value of A in the V in so much that it creates resonant harmonics at different frequencies that were not in your original input, therefore making the output here nonlinear with a higher A value, in this case 200 millivolts instead of 10. And you can see here you have 2 kilohertz, 3 kilohertz, and 4 kilohertz values coming out, as well as an increased DC value, even though we never changed the DC source or the DC value, therefore making it larger. And over here we have the transient response in time domain that shows as a linear combination of sinusoids, which here is the Fourier series equivalent. Now by Taylor series expansion we will show that it goes from linear to nonlinear, with A being 10 millivolts, that is our X in this case, out of the Taylor series expansion. And you see as you go up in higher order terms of X, these become negligible. That is not the case at 200 millivolts, as it is still a large value, as seen in the previous distortion graph with your other frequencies in your higher order X terms. Moving on to the amplifier circuit, one way to analyze this is to increase VB from 0.65 to 0.7 volts, and in doing so messes with the gain of the system, which is the V out over V in, which is a function of GM and R naught. And here we have our GM equivalent, and VB is equivalent to VGS. And this, as you increase this, GM will increase, which is our transconductance, by the way, and our R naught will decrease at a much quicker rate because this relation is squared, and thus, as you can see in this graph, decreases the gain of the whole system, because with R naught being smaller, the current will go through the path of least resistance instead of our load, which is our speaker in this case. Moving on to the gain of a two-stage amplifier. With one stage only, it is a common emitter circuit as seen here, and our lambda in this case is approximately 0, and R naught 1 is inversely proportional, so it will be a large value. Therefore, path of least resistance in this case goes through R1 and then as R out. The general amplifier of the circuit will have an open loop gain, and that will make our V out. Once we attach RL, which will close the loop, which is our speaker, it'll make V out our gain, our open loop gain, times V in over the voltage division of the resistors. And now the two-stage without RL first gets us a new a new gain value, which is a decrease in gain from our R out, which is R naught 2 in parallel with 1 over GM2. And this GM2 is an extremely small value now, and that becomes our R out in this case, because path of least resistance again. And this R out is much smaller than RL. Therefore, it's what we wanted. The current will drop and the voltage will drop across RL, therefore making a decent speaker out of this. And this is very practical in the real world because we are leveraging the first and second stage. In the first stage, we want to maximize the gain, so it will not affect R out very much. And from that, most of the drop will go across RL, thus making a good speaker. Moving on to the speaker itself, we have the permanent magnet, which is an iron core in this case, which has a nonlinear unique mu relation between B and H. And this is the equation of the load line for future reference. And we also have the coil. And here our relations of KVL are given here, and the conservation of energy is KCL from magnetic to electric circuits. And here we have our magnetic circuit and our electric circuit equivalent, which is just making the coil and the gap resistances themselves and making the Ni turns into an EMF generator. And we have the load line, which is basically the operation, finding your values of your magnetization and your magnetization intensity. And you can change this into an electric circuit by converting your B and H into I and V and making an IV relationship from these two load lines seen here. And then in the practical speaker here, we have a different sort of magnetic circuit. It is a permanent one magnetic magnet, and we have a wire coil around it. And the permanent magnet is a harder permeability material, which will demagnetize and magnetize at a slower rate. And the wire coil can magnetize and demagnetize quickly, therefore making the small fluctuations in current from what we get out of a speaker and changing the different frequencies very quickly, thus making the sound that we want. All right, everyone, I hope you enjoyed. Thank you.